session 10, torsion 2, but we have to go back to session 9 actually first to cover some of the things that we didn't get to. So we'll do that, but before we do that, I want to point out some things in the syllabus and some adaptations, if you will. So here we are, 611, session 10. All right, we can see that. So today we'll be discussing more on torsion and some indeterminate systems, and we'll also get to finite element, which will be hopefully fun. Tomorrow we'll start beams. That'll be Wednesday, and then Thursday we have some preparations for our accreditation process. So I'll be here for the first hour, but I actually have to be over there for the second hour. So what we're going to do there, I'll take attendance, but it's optional. So what we'll do is, if you show up on Thursday, I'll just count it towards one of the attendance. It's like a bonus, shall we say? If you're here, great. Then if you missed another day, we'll just count it. Does that make sense? Or we'll keep a track if you want to miss another day later. All right? Because I'm not going to be here for the whole time, so I'll let you all decide if you want to be here. Of course, there will be the video available afterward, or even during. Then, also, and this is kind of tough to swallow, I'm actually going to be for work away on the 17th and 18th. So I'll create the videos and you can do the work from home. I'll have the group meet. I'll have the other things, and you're welcome to come here and work together if you want, but or even watch the videos, whatever you like to do, but I'm not going to take attendance on Monday and Tuesday. Any questions on that? Yes.
You said Thursday was also the optional day?
So Thursday's optional, but you could get credit. I'll be here.
Yeah.
I'll be here for the first hour. But then Monday and Tuesday, I won't be here at all. Okay. So it'll be virtual. This should be the only, barring sickness, this should be the only times that I miss. Okay. And of course, if you have a good reason, please send a message to the Dean of Students. I guess there's been some issues with it, but what should happen normally is you send a message to Dean of Students, you send a message to me as well, and then we're able to evaluate excused absences or not. Okay. Any questions on that? All right. All the assignment due dates should stay as they are, given what we have. And of course, as you know by now, you can essentially get ahead if you want. You can watch the videos that are already there. The instruction hasn't changed that much, but it's fun to be able to interact and discuss things as we meet in the class. Okay, so let's go back to session 9. And everyone's like, wait, what were we talking about? Because that was before the exam, so of course we weren't really, that focused on torsion because it wasn't going to be covered. So what we had gone through discussing at the very end is, let's do this. The relationship between the change in the angle twist as a function of going along the length of the shaft with the shear strain. Okay. So, as a reminder, what is shear strain? Shear strain essentially is when we have some displacement and we have an angle associated with that displacement over this vertical length. So in this case, like a horizontal displacement and a vertical length and the angle there in that angle. Maybe I should go back. That's not the greatest explanation. But this is what shear strain looks like. Okay? Where you have your element that's being deformed, it's being essentially sheared strictly look at it from a more mechanics perspective, but from our perspective in this course, this should be a more than adequate image of what's happening. Okay, and what's interesting for us is that the shaft, when it has a torque applied to it, is an amazing example of a way to get what's called pure shear. So in this case, since we're not adding an axial force along the axis of the shaft, say in this x direction as shown here, we are able to twist about the x direction, apply some type of moment or torque, and that results in these rotations with some angles that we can look at and say, okay, there's actual pure shear strain involved. Okay? And we went through how you have a bunch of pizzas stacked, and then we looked at a slice of pizza in one of those stacks, and since there's some thickness of one piece of pizza, we can look at what the change in the twist from the top and the bottom would be, so this delta phi, and then we can go in and look at the angle, which is gamma theta z, which corresponds to the shear strain. Okay. Now, one thing we also discussed is that shear strain is dependent on how far you are from the axis of the shaft. So if you're right on the axis, there's going to be zero shear strain. That rho is zero. If you're at the outskirts or on the outer surface of the shaft, then we have rho equal to c. C is the parameter we choose to use typically, at least Hibbler uses, for describing the actual radius of the shaft, and that's where the strain is going to be the largest. The shear strain is going to be the largest. So there's a linear gradient between, say, rho equals 0 on the center of the shaft, on the axis of the shaft, and the outer surface. And the shear strain is going to be, so it depends on rho, okay, and of course it depends on the slope, okay, the d phi dz, but the shear strain is not going to be different, say, closer to the wall versus farther from the wall. Yes, the angle of twist, which we'll talk about today, is going to be different. It's kind of like a spring, right? The longer the shaft is, the more it twists. Right? We've seen this kind of thing before. The longer the bar was, the more displacement we had. Okay? So we start to see more analogies here. But it is, of course, dependent on rho, and it is, of course, dependent on the amount of torque that you are applying. And we're going to get to how we figure out the relationships between torque and angle of twist and shear strain. So back to the angle of rotation, what we're saying is, yes, the angle of rotation does depend on how far you are from the wall, essentially, or how far you are from the constrained side. And if you're halfway down the shaft, right, then that's going to be half of the total twist at the end of the shaft. And what is the shear strain? Okay, at a distance from center line rho at z equals L over 2 and z equals L, well, we just said it's not going to be dependent on z, right, this distance from the wall. And it is dependent on rho, and so we can, if we know what the angle of twist is, and we know what the length of the shaft is, it's 1 meter, right? That d phi dz term that we had earlier, okay, this d phi dz term, that just becomes phi over the length of the shaft, right? Because it's a constant slope. The shear strain is a constant, or the d phi dz is a constant slope, constant value from z equals 0 to z equals L. Okay. All right, so now let's get into something new. we have described now, maybe almost ad nauseum, what shear strain is, okay, as we see here. And we also said that the maximum shear strain is when we're at the outer surface of the circular shaft, the cylindrical shaft. And so we have that occurring at rho equals c, and we said, okay, if I am not at the outer surface, but I know what the maximum shear strain is, I can do linear interpolation, essentially. That would be the rho over c, to figure out what the what the shear strain is inside the cylinder. Well, we've also had the opportunity to introduce this constitutive equation, which is that tau is equal to g gamma, right? This is, again, analogous to sigma equals E epsilon, but tau is equal to G, all right? So now, because we have this linear relationship and we have this linear relationship, we can also say that a tau max, right? So a gamma max, assuming that the shear modulus is constant throughout the material, and that's a pretty good assumption for this class. And for linear isotropic, isotropic just means, you know, same throughout materials. And we talked a little bit about how G is equal to E over quantity 2 times quantity 1 plus nu. Right? And we'll derive that later in the course, but that for now is the relationship between E and G. So we have a relationship that says, okay, I can also relate the maximum shear stress to local shear stress. And again, it's going to be dependent on how far I am from the central axis. Now, let's take a look, and as a reminder, okay, this is the shear strain, right? And corresponding shear stresses on an element would look something like this, right? You can see that there's a shear stress that's pulling this way, and there's a shear stress kind of pulling this way. These are in opposite directions, and then to make sure that the element is not accelerating rotationally or does not have angular acceleration, we need to have corresponding shear stresses to balance the rotation out as well. So as we begin to think about shear strain and shear stress, right, we want to be able to relate these quantities to each other, and we can, at least for pure shear, we can through the G. Now, with a shaft, if we take a slice, so now we were on a slice of pizza, okay, or not, sorry. If we select a pizza, all right, that is stacked in our shaft, this is what the shear stress would look like across the face of that pizza. So wait, does this make sense? Well, just a few minutes ago, what did we say? We said that the shear strain is proportional to this ratio of rho over c, right? And at the middle, the shear strain is 0. Well, we also are saying that the shear stress has the same behavior, this rho over c. So look, if we're at the middle, there's going to be 0 shear stress. But as we get to the outer surface, we reach our maximum shear stress. Okay? And again, sometimes it's very useful just to think, I'm applying a torque, what is the deformation of the structure that I'm applying this torque to, or I'm applying a force, I'm applying a load, better said. What does the deformation look like? And then once I kind of have an idea in my head what the deformation looks like, I can start to maybe put some grids and draw elements and see what they're doing in terms of their deformation. Okay? So what's happening here is that you have this torque being applied. All right, let's say it's coming out of the board, and you're obeying the right hand rule, right? Because this TZ or this Z, we're going to say that's the, coming out of the face. That's going to be positive. And so what we end up getting is this gradient in shear stress, okay, as a function of rho. Now, if I make a little dA, right, I say, oh, okay, this shear stress is acting over this little times aerial element, okay? This is kind of going back to what we talked about with the traction vectors at the very beginning of the class. Well, maybe not the very beginning, like the second day, I think, where we were discussing how we had tensors and we had these traction vectors, and the components of the traction vectors are these stresses, right? And up to now, we focus mostly on sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z. Now we're focusing on, okay, maybe tau 1, 2, tau 2, 3, tau 1, 3, okay? And it's acting on an area. So look at this. If I say I'm going to integrate over the entire surface of that pizza, okay, that would, so like it'd be like 0 to A, for example, but I didn't write that. Okay, so that's going to be the dA, right? And I have these moment arms, rhos, and I have a tau acting on this dA. So right, tau times a dA, right? That seems to seem like, oh, maybe that's like a little microtorque or something, right? Then I can figure out what the total torque is, okay? Or the rho tau dA, better said, right? That's like a little torque acting on an aerial element. So now we have ability to integrate this expression to figure out what the applied torque to the system is. And you can then begin to see, well, let's go ahead and substitute in this expression for the shear stress. So boom, that comes in there. And then we have rho and rho, okay? And that is going to give us a rho squared, right? And that can vary. And this tau max is a constant because that's what you have at the surface. C is a constant, so I can pull them out. And here, this quantity, integral of rho squared dA, okay, ends up being something that we call the polar moment of inertia, or J. Okay. So this, you could think of, there are different ways to approach this integral. For our purposes, typically we're just going to use relationships that we give you in the class. But we also will, especially when we'll do some examples where we integrate this type of double integral, right? This is with respect to area, right? So here you can think of, okay, I'm going to go from 0 to 2 pi, all right? That would be one integral, and the other integral would be 0 to c, okay? And then I need a r dr d theta for dA, okay? Or rho dr, right? Am I making sense? I think I'm making sense, right? So one way to think about this, right? And again, you will not really need to think about it this way, but we can think about it as, maybe I can't zoom. Okay. Okay, here we go. Yes. All right. So, one way to think about this is that J is equal to the integral from 0 to 2 pi, 0 to c, rho squared, and then this is r dr d theta. Okay. And on the next slide, there will be a relationship, but you see, now we've got, oops. It's r dr d theta, but it's really rho d theta, right? Does that make sense? So it's an r cubed, right? So you're going to integrate that, and you're going to get a r to the 4th term. And so this polar moment of inertia, or polar moment of area, is actually a better way to put it, because this is not density, this is a radius, okay? But and so we're really looking at, that's really, we should write the polar moment of area. Okay. really, it's, what did I just do? Interesting. Okay. But you'll see, if I multiply by density or if I do this with mass instead of area, then that's really where you get the polar moment of inertia. Okay. And you've seen that before if you, like in dynamics, right? You've seen this because you have rotation, right? So it's analogous, but it's over the area. Or you've seen it in your differential equations class, right? When you're doing second order systems, where you had the I theta double dot, right, equal to whatever the summation of the torques. Okay, the point is this is a useful way to then figure out what the shear stress is as a function of the torque and the geometry. Notice the shear stress is independent of the shear modulus. No shear modulus in here. Okay. We did kind of use that information, okay, to be able to jump from here to here, right? Because we knew that these would be related to each other, but the shear stress is going to be dependent on the geometry. What does this remind you of? What other systems, right? The bars. Whenever we calculate out the stresses, right, we don't care what the elastic modulus is, okay? Unless they give you the strains. If they give you the strains, then you're going to go work back through it. But if you're given an area and you're given a force, right, you can calculate the stress, the normal stress, the axial stress. So here it's analogous. If they give us the radius of the shaft and the torque, we can figure out what the shear stress is going to be. Okay. We have this other term, this J term, but you can also, and so this would be the max when it's at the outside, but also you can figure out what it would be on the inside, right? As rho is less than C. So polar moment of area. So here you go. This is kind of this is kind of the only time we're going to do this all out. Okay, but you can think of that double integral, solving that double integral, and you're going to get, or we're going to get, that J is equal to pi over 2 times C to the 4th. We're going to have something also that we call the second moment of area later. Okay, so this is the polar moment of area, and we give it the term J. There's going to be something that's called I later, okay? And that's called the second moment of area. It's for beams, and it's very interesting. And one of them is pi over 2 radius to the 4th. The other one is pi over 4 radius to the 4th. I comes before J, so I is less than J. All right, so you're gonna, just prepping you that you're gonna see this, and you're gonna be like, is it pi over 4 or is it pi over 2? Pi over 2 because J comes after I, and J is greater than I. Okay. Anyway, but you can see that we can take these annuli as we move up, and we do the integration, and this is what we get. Okay. Now, what happens if I increase the radius? Well, and I'm talking about what happens to the shear stress if I increase the radius. Well, you're like, oh man, TC over J. Well, C is getting bigger, so the shear stress must be getting bigger. But J has a C to the 4th in it. So as we increase C, okay, the shear stress goes with the third, or with the inverse of the third power. Okay? So the shear stress will go down. And that makes sense, right? Again, we go outside, we get a branch off a tree, hopefully on the ground, right? We don't kill the tree, right? On purpose for this experiment. But, the larger the diameter of the shaft, or the stick, or the trunk, or whatever it is, get it to break. That's because the larger the diameter for a given amount of torque, the lower the shear stress. Now, one way to think about this, right? Yeah. So the lower the shear stress, and you can think conceptually that J is what is J. This polar moment of area is like resisting the torque that we apply. Okay. Now, shear stress or shear strain can also come out of this torsion formula. Okay, so yeah, so I guess I should say that. Maybe I didn't make that clear. This one is nicknamed the torsion formula. All right, I don't know why they put it with shear stress and not shear strain, but this is the world famous torsion formula. All right, and we are lucky that we live in New Jersey, where we have our esteemed fellows at TCNJ. All right, you might have been taking this class there. We have actually there's a nice connection between Rutgers and TCNJ. If you want, I'll tell you what it is later. Okay, but this is the TCNJ formula. Okay, that's how I think about it. All right, the torsion formula. Okay, so so this is just a summary. Plus now, okay, if I know the shear stress, then I also know the shear strain. So this is like a modified version of the torque. So this is the TCNJ formula, right? Rho is just inside and not, and C is the maximum, right? And so if I have the shear stress, then I can divide by G, the shear modulus, and get gamma, and that's what you have here. So T rho over JG. I don't know why I don't remember this one. I would have to, I don't know. But this is kind of analogous to plea. Okay, I love plea. I remember plea. So for some reason, because of TCNJ, I think it's shear stress, and then I'm going to have to write it out probably every time and divide by G because I know Hooke's law. But anyway, I mean TC over JG. It's not that hard to remember, I guess. But that's for the shear strain. Let me just do this. So not. Okay. Thank you for your patience. All right. So yeah, there'll be a question on the assignment. All right. Actually, I think I delayed this appropriately. If I didn't delay it appropriately, let me know. But if you have a torque T, what is the shear stress at a distance rho from its center line? Well, that should just be this one right here. Okay, T rho over J. Now, notice this question said something interesting. Internal torque. I kind of glossed over that when we did the integral of the rho dA, okay, to figure out what the torque is and how it relates to, or the integral of rho tau dA, okay, kind of glossed over that, but we're not going to gloss over it much anymore. Just like it's safer to think about the internal forces and bars, it's safer to think about the internal torques in shafts. Okay, when you're calculating these quantities. Okay, so for handling this type of problem, okay, we first think about the external equilibrium. Then, well, I guess, and in doing that, right, we're going to do things like define our coordinate, system or axis, and apply Newton's second law. And in this case, it's the sum of the torques is equal to 0. Right? So this should be a very similar pattern. And remember, there are the three pillars of solving problems in mechanics. Right? The equilibrium, the geometric compatibility, and the constitutive relationships. We're just talking about equilibrium at this point. Then we should take a slice, and that will allow us to use method of sections to then calculate some things internally. All right, so this was the first. Sorry, I guess it's a little bit out of, but this is external equilibrium, right? And then we're going to take a slice, like we've done before, and it's probably a good idea to define the coordinate system or axis coming out of the board. Coming out of the slice, I'm sorry. Coming out of the board arguably would be on this side, but anyway, you see this is going to be, we'll call that positive. And that doesn't, we did this before, right? That doesn't unnecessarily line up with what we defined for our global coordinate system when we did external equilibrium. And we can then write an internal torque AB that follows the convention here, and that allows us then to relate it to whatever, the other side is. Or, this is the Jeff Hansen cover-up method, right? So, we covered up the right side, and then we just look at what's going on the left. So we do the equilibrium, so we now can write what it is on the inside, that it's TAB is equal to TA. And yeah, when I was being a little bit, how do you say it? Lackadaisical, I guess you could say, a few slides ago in terms of, that's the external torque, where I didn't really say, I should have said, that's really the internal torque on the pizza. I kind of imply that, but this is making it more definitive and more formal. And likewise, we can take a slice and then have it coming out toward us. So this one is going to have we'll say a positive z coming out toward us, and we'll define TAB to be in the opposite direction. And we've done this before, right? This was session 2. All right. And we know that TA is equal to TB. Okay, so this is how we go about figuring out the torque that we should apply or we should put into the torsion formula. So something like this, we have multiple torques applied to a shaft. Okay. And yeah, it's probably, some of you are like, oh, I know what this is, just by looking at it. And like I said, ignore F because this was from, I don't know, was this from this is from our final exam. So by the end, all right, we can handle systems that have both axial loading and shear forces. Right? We'll talk about what's called combined loading quite a bit, actually. But here, even before we do anything, right, we notice that step 1, external equilibrium is satisfied. Right, it needs to be. Right, you see, if I define, let's say this is the positive z coming out here, right? So then this TA is T, this TB is minus T over 3, and this TC is minus 2T over 3. Everyone can see that, right? So I don't even have to give you, if I didn't give you this, you would be able to calculate it out if I said it was an equilibrium. And then if we use the cover-up method, and we're looking at what's inside TA between A and B, right? We'll call that a T subscript A and B. We can use the cover-up method. Probably easier to cover up the right side, right? And then we just have an external TA, which is TA. But when I've covered up this side, right, then I've got something coming kind of inish to the board in the right-hand rule, and that would be the TAB. And TAB is going to be equal to TA, which is equal to T. All right. And we can similarly do the same thing over here. Probably better to cover up the left side if I'm interested in what's happening between B and C. If I cover that up, then I'm just going to have 2T over 3. All right. So that's kind of what's on this slide. Okay, just a little bit, more algebraic-y. Oh, but I guess what I should say, since the point is, once we know what the internal torque is, like so, say this is TAB in here, right, which is equal to TA, which is equal to T, right there. Then you plug it into the torsion formula, and you have the result for what the shear stress might be at the outside of that shaft, or if I give you, if you were given a row, you know, some distance from the axis of the shaft inside, you'd be able to figure out what the shear stress is, and thus you would be able to figure out what the shear strain is too. Okay, so that's how you'll do this problem. And so this one was calculate the shear stress, the maximum shear stress, so that's going to be TC over J, halfway between points B and C. And then this one is going to be about calculating out what the shear stress is at a radial distance halfway between a simulating outlet. So if you have a diameter of 1.4 centimeters, the radius is going to be 0.7 centimeters, right? And so half the radial distance is going to be 0.35 centimeters, right? So just telling you because I would make that mistake, and I've done it many times. So just diameter, right? Radius, common senses, but frustrating moments in front of Canvas. Yes?
So for that question, what if the force wasn't equal to 0?
Okay, yeah, good question. All right, so if the force was non-zero, okay, then you would have a normal stress, right? And what's going to happen in a few of our meetings soon, okay, is we're going to have situations where, okay, so I'll just tell you. Let's say that you have an element on the top, okay? So we're looking down. And what is the shear stress? Well, the shear stress, if I take this element over here, okay, how do I think about the shear stress? I think about writing out the shear stress on this element by the deformation. So I have a torque that's moving this way. So that means, and it's moving this way on this side. So I'm going to say the shear stress, whatever it is tau there, all right? And then on this side, on the opposite face, it's going the opposite direction, okay? And then these got to meet each other like this. The arrows always meet each other. So now I've drawn the state of shear stress, okay? Does everyone see this? I'm glad you, we're going to go over this ad nauseum in the next little bit, all right? But since you brought it up, we'll talk about it. So what happens is if I have a force that's non-zero, well, what's the stress? Then if let's say F is greater or it's just not equal to 0, because it could be compressive or it could be tensile, then we have a sigma that's going to be equal to F over pi d squared over 4, all right, or pi r squared, whatever, okay? So in that case, what happens is on this element, I actually end up drawing sigmas like that. Now, okay, how do I put this? Remember, even on exam 1, I asked, what's the maximum stress, or what's the maximum force, what's the diameter I need, right? Can't remember what I wrote. What's the diameter I need, right, so that it does not yield? Okay? So I was already, even though we haven't talked about failure criteria yet, we're already to the idea that if I hit the yield stress, or the yield strength, then things are going to, quote, fail. Similarly, right, we said we can draw these shear stress diagrams, or the stress strain diagrams. We can do the shear stress, shear strain diagrams. Again, they hit a yield value for shear stress. Okay? So if it's a pure shear situation, okay, so there's no sigma, then I can say, all right, I can figure out what the shear stress is, and if I hit the threshold for the material, I fail. If I below the threshold, I'm good. One other fun thing we're going to do in this class is we'll be able to figure out what the equivalent stress less than trivial. Right? Now, if sigma is really small relative to tau, then whoopie-doo-dah, you can kind of ignore it, right? But what we'll do in a little bit is we'll show you, oh, yeah, I can figure out what the equivalent stress is on this element relative to what you have in a tensile testing machine. Okay? Because that's what you do, right? We tensile test our materials, we get these yield strengths, and we want to know then for a given structure what the state of stress is so that we can relate it back to the yield stress, the yield strength of the material from a tensile test. Okay, good question. Did I answer? All right. Yeah. Once again, you got me going off on a tangent. All right. So that is the end of session 9. Now we're going to go into session 10. Okay. We can kind of skip the recap, all right, but what we're going to cover today, or now, is shear strain, torsion, some material properties, how we relate torque and radius. What do you know? You know, radius is very much related to torque, right? We'll talk about angle of twist. Then we will talk about gears, which are really complicated and they're fun, and I was mean back in 2015 and 16. So you'll see that there's some gear examples. Maybe we could probably do a simple one. I don't think I've had the courage though to give a geared example in the last couple years. We'll talk about distributed torsional loading, and then we'll talk about indeterminate torsional systems. And then we'll do some finite element analysis. So some fun, interesting stuff. And I did not bring a mouse for doing the finite element. So, well, we're not there yet. Maybe, yeah. Actually, if you have a handy one later, that'd be great. Okay. Yeah. Okay. Great. Okay. So yeah, this is review. Here we go. So anyway, by the end of today's, so there was a time when I did more flipped classroom stuff. So it was like, oh, why don't you take a look at the video before? I've learned, well, I don't know. You can tell me, but people kind of like to discuss this stuff and go through things. So we're not doing too much on the flip it end. But today we're going to talk a little bit about how to think about the twisting of a shaft between two walls. We're going to be able to relate the torsional load to the diameter of a shaft. We'll talk about angle of twist. All right. We won't talk about normal stresses induced by torsional loading. Not much. I guess you could actually, we kind of do indirectly, but that's not the answer to the question. And then we'll talk about distributed torsional loading along a shaft. All right, so by the end, we should do all but that one. Okay, you've seen this, kind of, at least the material on the left. We've kind of talked about this as well. All right, but this is the formula that you want to write on your formula sheet. And this is different than that one minus the, when we're talking about the dilatation, right, and the volumetric strain, there was like that denominator that was like 1 minus 2 nu, right, and we said it explodes here. So in this case, it doesn't explode, right? If I give you 0.5 here, it doesn't explode, but of course, well, maybe not of course, the nu typically is going to be, somewhere probably between like 0.1 and 0.5. Can't be greater than 0.5. So this is the shear modulus. Yes, okay, good. I did write out that's what it's called. And it's related to both the elastic modulus and the Poisson's ratio. Conversely, right, if you need the elastic modulus, right, I mean, I guess this is maybe trivial in some respects, but, E is equal to 2g times 1 plus nu, right? So that's useful. If you're given 1, you can go back and forth between, or I guess poor Poisson ratio. I just think of Poisson ratio as not moving that much. So I didn't define what Poisson ratio is in terms of E and G, but that's typically 0.3 or something like that for our materials. So we can also relate the shear stress, okay, and the shear strain, like we said before, through Hooke's law, and if you like, we can do it through this nice matrix, okay, like you see there. Now, this may look a little scary, all right? Remember how we had though, and that looks even scarier, all right? Remember though, we said that we can take these rows and these columns, right? And we can figure out what epsilon x is, so that's not that scary, all right? This is that constituent relationship that goes one step behind the uniaxial Hooke's law, okay? Where we said, okay, if you have some orthogonal normal stresses and you know what the Poisson ratio is, it's going to affect the strain in a particular direction. So the first three rows here are just the epsilon x, epsilon y, and epsilon z. Okay? The next three rows, okay, are going to essentially give us a relationship between gamma and tau. So this is the Hooke's law, okay? And it says, all right, we don't really need to care about the normal stresses if we're calculating out the gamma. This is just tau equals g, all right? That's all it is, except flipped. Now we have gamma equals tau over g, okay? The ones, right, and here it is. Okay, so the ones below are, well, they're good to know, but you're not going to probably need to use these in the class, okay? But you see that if you were given a state of strain, that's actually not true. We're going to do stuff, yeah, we will do stuff with strain gauges a little bit later, so we will kind of use some aspects of these relationships. So here's the thing. If you are looking at a block of material, I can't really tell you what the stress is just by looking at it. Okay, I mean, I mean, if it's like translucent, so there are some materials that they change how they polarize light as they are strained, okay, or stressed. But typically, right, I can't really look at this table. I mean, I might have an idea of what the state of stress is, but quantitatively, you know, I don't know what it is. But we can put strain sensors, we can measure how much things are straining, and then we can try to figure out what the state of stress is. Because things fail because of stress, right? And stress is related to strain. Okay? We also have issues where we want to satisfy certain geometric requirements, so we are still interested in strain, but what's cool is that we can put these strain sensors on objects and try to figure out what the stress is. Turns out it's messy business. So we've worked on some stuff where we were trying to make wireless strain sensors, and we have at least one master's thesis on this, and a manuscript that didn't get published yet. I need to get on that. Sorry, NASA. But yeah, with some work looking at how we could do structural health monitoring with strain sensors that are wireless is of interest, in particular to people who work with pressure vessels, because you don't necessarily want to drill a hole in a pressure vessel, put wires in, and then measure what the strain is. We'd like it to be able to interrogate through the wall and be able to figure out what the state of strain and stress are. Of course, An alternative is to put the strain sensors on the outside of the vessel, which also is not a horrible idea. All right. So, remember session 1? You see it says session 1? Isn't this so exciting? We're coming back and we're doing things that we did already. Do you remember what we said here? We said that shafts are used for transferring rotational power, and we can think of them as springs. And we said that what their dimensions are. We said that we had steel and plastic. All right. And then, you know, they can be in drive shafts and different manufacturing processes and turbojets and various aerospace structures. And we came up with a scaling relationship, right? How does the load scale with changes in diameter or cross-sectional area and length? And does anyone remember what we said back then? Close, not quite diameter squared. Cubed, right? Yeah, it was a diameter cubed, right? So we said the supportable load scales with diameter cubed or area to the 3 halves. Okay. And we also said that the supportable load is independent of length, although longer shafts are going to potentially have issues with buckling, and they will rotate. We'll have larger angle twists, right? So this is going back to the first day. We now know the mechanics to be able to give some quantitative answers. Okay, so we did this, we did this, we did this, we did this. All right, we did this. Whoops, this is in the wrong spot. What happened? What just happened? Okay, I don't know what just happened. Okay, what did just happen? Okay, so I need to, maybe we should, okay, well, how so, says the cow. How now, cow? All right, well, we have torsion formula. Right? And what is the torsion formula? That is TC over J. Okay? And then what did we say J was? J is pi over 2 C to the 4th. So tau is equal to TC over J, right? So this means that the shear stress, right, that we are developing is going to go as 2 torque pi C cubed. I didn't lie. I said it went with the diameter cubed. Right? And now we know why. Because the material is going to have some shear strength, okay, or shear, yeah, so shear strength, right? Let's say we have some shear strength tau y, right? That's going to need to be greater than, or if that's less than or equal to, you know, tau, then we have failure. So we've done, that's the beauty of the torsion formula. Okay, any questions? Comes full circle. All right, so I made a mistake. I don't know why this is there. Okay, but how do we think about angle of twist? And I'm sorry, this is a little bit choppy. I messed up this slide, but what is phi here? Phi is how much angle rotation we have as we move along the shaft. Okay. And we have an expression that relates the gamma to a rate of, or a derivative of phi as a function of the z parameter along the axis. So we can reorganize and say that d phi is equal to rho dz over rho. Or did I say rho? I mean gamma. Okay. So is there a constitutive relationship we might want to throw in here? Yeah. Tau equals g gamma. All right, and then we plug that in to this equation like you see there. We can also bring in the torsion formula, where tau is equal to T rho over J, or Tc over J if it's at the outskirts. We combine these, and we get this d phi is equal to tau dz over Jg. The rho's actually cancel. What do we do? Then we integrate this. And we get phi, right, is going to be equal to this integral from 0 to some length, and tau dz. And look at this. Phi is equal to T dz over Jg. What is this analogous to? This is analogous to integral of P dz over Ap. These are not multiplications, of course. It's just saying that these are dependent on these parameters. So, you know, on your formula sheet, you write just that this phi is equal to T dz over Jg. So what's of note worth, or what's worthy of note? Well, it's possible that T or J or G could vary as a function of length. And this T is going to be the internal torque, right? Just like the P was the internal torque. Okay, so we've got now, did I do that? Oh, I skipped. If we go from 0 to L and the torque is constant, then it's just TL over JG right here. You see that, right? Integral, if I go from, it's just, this is this right here. That is, right, the integral for constant torque internally. And in this case, is the torque constant across it? Yeah, it is, right? If I have a torque being applied at the end, there's a reaction torque that's opposite to it, and as long as I don't have any intermittent torques applied to it, then yeah, it's going to be just dandy. It's going to be fine. So the angle of twist is TL over JG. And what's that analogous to? That's analogous to delta is equal to phi. So phi had a spring constant, EA over L. So does TL over JG. I don't have a good memorization technique here. I don't know. TC and J, I was like, okay, I understood that one, but I don't know the TL or JG. I don't have a good mnemonic there. But this is an important relationship, and of course, if we have torque equals K phi, right, just like you have K delta, then KT is equal to JG over L. And if we increase the J, and if we increase the G, for a given amount of torque, it's going to twist less. All right, and if I increase the length, it's going to twist more. So we're just using some math and physics to explain observations you've known since you were a young child playing in the dirt with sticks. Okay? So the constituent relationship relating torque applied to a shaft with angle of twist is which of the following? It's just this one. TL over JG. Okay. All right, now, just remember, like we were talking about springs in series. Okay, so springs in series, maybe I should just bring this up again, or maybe not. Everyone's probably sick of springs. Okay. But if I have this system, I wrote the spring analogy before I actually wrote the mechanical system, right? And there's a force here. The total displacement, right, here would be essentially what? The F, if this is L1 and this is L2. Let me do this a little bit better. Okay, well, I lost it. So let's say this has length L1, this has length L2. Then, you know, this is going to be FL1 over EA. And this is going to be FL2 over EA. Why? Because when you have two bars in series with each other, the forces are the same internally for both of those bars. So the total displacement, right, so this would be delta 1, this would be delta 2, right? The total displacement is just going to be delta 1 plus delta 2. This equation is saying the same thing, except we have two shafts that are connected to each other and they're in series with each other. This is what series shafts look like. Okay, they look remarkably similar to series bars. And I have some torque, and so that torque, we just did some problems, right? Torque doesn't care about the cross-sectional area. It's going to be the same in both of those. Okay, the internal torque. But the stresses could be different. All right, that's truth. Okay, and the angular displacements can be different too. Okay, if the J's are different. So just like we had here, we can write out this phi is equal to the sum, right, of the rotations of the individual sections. So again, it's kind of common sense, but there's the math, and we've done the physics now to explain that, the mechanics to do it. Yeah, this is the spring analogy, right, that we have here. So the spring constants are going to be what? They're just like we have the EA over L, right? Or we say, okay, you have a K times phi is going to be equal to a torque. All right, so that's going to mean that the KT, or the spring constants for these shafts, are going to be J1G over L. So just like that. Those are the individual spring constants. So the torsional spring constant for the entire system is going to end up looking like not that. Okay, that's not right. Because that would be in parallel. K should be equal to the K1, K2 over K1 plus K2. I'm glad I can think. I'm not saying I'll catch every mistake, but I'm glad I'm not like completely out of it. All right. Any questions on this? This, of course, is the, you know, and maybe I should even be more careful here. That's like the phi, right? So this is saying that, okay, if you have a phi at the end, right? And I have a KT, I'll do KT. That's going to be equal to the torque. I don't think as much about these shafts and the springs in series and parallel as much, but it's still helpful. What do you think springs toward? What do you think this? What is the physical analogy for torsional springs in parallel? What would that system look like? So here we're saying the torques are the same and the displacements are different, right? That's what we've been saying about the springs in series. What are we saying for a parallel system? Yes, go ahead, Dylan. You have an idea.
Maybe like different sized gears that are connected along the same shaft.
Okay. All right. Yeah. All right. Yeah. So I mean, I think you could come up with some type of equivalent network using gears. Interesting. Any other ideas? How could you have shafts having the same amount of rotation, but potentially holding different torques? Yes, Dylan?
What if it was like a cone rotating?
Okay, cone rotating. All right, we're getting close. So I guess the analogy or the I'll just open up keep. And this is where you get to see my bad drawings. Okay, what I would think of is, let's say we had some shaft like this. Then I would actually draw another shaft around it. Right? And it would be like some type of annulus, just to make them two separate ones. Okay, so like you have this here. All right. And you have this face there. Okay, see that? So now, and then I'd be applying some type of torque, like I have some type of wall here, you know, something like this on that side, and then I'd be applying some type of torque, so to make it right hand rule, like that. That would be kind of a way to be able to put them in parallel with each other. That's a little awkward though, but it's not bad. Okay, so let's go on. So this is a physical system with shafts in parallel. Okay. So now let's talk about relative displacements or deformations. Better said, I guess. We have the bar. Okay. And if I'm interested in delta A versus B, I could write it as going to the left. And it's probably not a bad way to do it. It's not necessarily as convention or as mandated, I guess you could say, as some of the other types of systems that we've talked about where you're taking a slice, but I could write it like that, and I could also write delta B relative to A, okay? And I could have the forces going in the same direction, okay? Or I could have forces coming in. So first off, what would we say the relationship is between delta A slash B and delta B slash A? And we're thinking about the magnitudes here. They're going to be equal to each other, right? They're drawn in other directions, but if we think of their magnitudes, they're just equal to each other. Now, what are the relationships between F1 and delta A relative to B and F2 and delta A relative to B? Yes, right? So we can see that since F1 is in the same direction as the arrow I've drawn for the displacement, then we have that F1 L over EA will be this relationship here, and minus F2 over L, minus F2L over EA would be the relationship here, right? What happens in a shaft? Well, we can, again, choose some conventions, and here, these are externals, so you can kind of pick your directions for these torques and whatnot, but it's probably not a bad idea to say, okay, I'm going to do the displacement coming out, right? But then I could have a torque, right, that's following the right-hand rule here, and I have 4 torques that are going in the opposite direction of the right-hand rule. Okay? So now the relationship between phi AB and phi BA, again, has them equal to each other. And again, I can think of phi A relative to B as being in the same direction as torque, or the positive torque when drawn this way will be a positive phi, whereas a positive T2 would be a negative phi. Right? So this just gives us a kind of a little bit of background in terms of how we can think about the relative twists, okay, with respect to conventions. Okay, now let's do this thing. Wait a second. That is not. Okay, yeah. Okay, a little bit more on this. Yeah. So first, we can go back to this example, all right, and we can think about, okay, what are the internal torques, and we can think about these angle of twists. We can also begin to think of, just like we did, we summed up the twists in the different sections. We can think of, if I want a C relative to A, right, I can think of C relative to B plus B relative to A. And of course I want to define those to be in the same, I want to be careful and define those in the same direction as I'm going along. And you can see here, okay, that we have the opportunity to kind of add things up, right? And we can figure out what the total deflection is of C relative to A. Okay. Now, if we begin to look at gears, this is where things start to get dicey, right? Let's say that we have a shaft that's in a wall. Has anyone ever been to a museum exhibit where they have like a motor spinning and they have a bunch of screws, or not, a bunch of gears, and they show that the displacement and like this, eventually the shaft like goes into a wall because the displacement is so small with the gear reduction that the shaft doesn't noticeably twist. Okay, well anyway, this, I don't know if they still have one. The MIT Museum had one in Cambridge that did this a long time ago. At least that's what I recall. So this, though, is not quite that system. We're not going to have that. Well, you could, but here, let's say that we don't have that much of a gear reduction. And we are interested in knowing what the displacement at the end will be if you give a torque. How's this relevant? This is relevant to, say, a gear train, right? You may not care too much about how much twist you have, but you definitely care about whether or not your shafts in your gear train are going to break. And in DMC, design mechanical components, you also talk about teeth and how they line up and whether or not the gears are going to be experiencing too much stress and how they're going to fatigue over time. Okay, so you want to, if you're designing a gear train, you want to be able to make sure that you have the appropriate sized teeth to be able to support the loads that you're going to be exposing the system to cyclically. And there's a difference if the gears are constantly going one way versus if they're going back and forth with alternating stresses. Anyway, how in the world do we approach this? Well, and which of these is correct? The answer is very painfully. No, we'll try not to make it too painful, all right? We have, the short answer is, I should just probably write this down somewhere. I'll write it on the side because there's nothing over here. Make sure we have geometric compatibility. Okay, and this comes in the form of the linear effective distance that the gears rotate, okay, needs to be the same. All right. So we'll talk about this. So linear effective distance of wheels or gears. So often when you do these problems, this could be a geared system or it could be like a wheel system that doesn't have any slip. All right, but it's about the radii. It's about the relative radii. And then the other thing is, make sure we do equilibrium of contact forces between the wheels or the gears. Okay, not equilibrium of torques. Okay, we'll talk about this in a minute. Okay, and if this one doesn't have it, but often, like if you have spinning systems, then we also think about conservation of power, or very close to that. So if someone's asking you, oh, this gear's spinning at this speed, this gear's spinning at this speed, and what's the power transfer in the system? Or that's not the right way to say it, but what are the relationships between torque and speed? Okay, so where is this? This is super important, right? Because we have lots of systems that have a rotating motor somewhere, and they have an output, right? Automobiles, primary example. Okay, and so you have power being generated by the electric or the internal combustion engine, right? And that power is more or less conserved, and then it gets transferred to your wheels. But the motors or the engines, do they have high torque or low torque typically?
Relative to.
Well, yes, relative to what I can do, yes, that's true. Relative to the torque at your wheels, is the torque coming right out of the motor high or low? It's low, right? Because you've got a lot of speed, right? You've got your tachometer in your car. Well, some cars have tachometers, not all, right? But you've got, that's the engine speed, right? That's how many revolutions per minute you have. Your wheels are not spinning that fast, right? There's a reduction system in there, a transmission that is making it go much more slowly, but the torque has gone up. And the power loss through the transmission is usually very low. Okay? What you're trying to do is get the peak power of your motor, whether it be a combustion motor, or an engine, internal combustion engine, or it be electric motor. You're trying to get that optimal power, and you're shifting gears to get a nice transfer of that power to the wheels, an efficient transfer, right? And that's the beauty. And that's actually the beauty. Did we already talk about this? We already talked about this, right? The beauty of the electric motor. We're gonna talk about this. Okay. Again, this is for your good to know file. All right. We didn't talk. I didn't go on this. I didn't go on this tangent with you. I must have. I always go on this tangent. Okay. So, anyone heard of torque speed curves? Okay. What do they look like, typically?
I mean, you want them as flat as possible. They kind of go up and then go back down.
Okay. All right. So that's a power speed curve.
Okay.
All right. No. This is good. This is good. Right. For electric motors, if this is torque and this is speed, angular velocity, what do you think the relationship looks like for an electric motor?
It's going to be linear.
Good. Yes, linear is correct. And what does it look like? Has anyone played with an RC motor before? I don't necessarily think I can suggest that you grab the end of a motor and you use your hand as a dynamometer, but any ideas? Yeah, you did a thing.
Yeah.
You did a thing. Okay, that's the thing. All right, this is what it looks like. This is called the stall torque. Okay, that's not even, that's because it's in the corner of the screen, okay? That's my handwriting is so bad. Right, that's a stall torque. And remember that power is equal to, I got so many other things I got to tell you about. I should probably not do this, but this is interesting, and you should know these things as an engineer. Okay, power is equal to torque times omega. That we have talked about in this class. Okay, so what ends up happening, okay, power equals torque times omega. I've got a linear relationship between torque and speed, right? So I could write something like, mx plus b. Now in this case, this is positive and this is negative, right? That's negative, this is positive. You can see that, right? Because it's got a negative slope. So the power is equal to torque times mx plus b, all right? And that ends up being, actually I should, no. Usually it's written like you were saying. This is correct, but usually what we do is we write it in terms, it becomes a function of speed, okay? And look, this is going to be, where's my mousey? This is going to be a, omega, right? That's the x, right? So it's m omega plus b. So this ends up being a second order. So this ends up being proportional to like some omega squared term. And it ends up being an upside down parabola because it was negative. So like what you're saying is it usually ends up looking something like this. Right? And this is power as a function of omega. Right? It's good to have someone with some real engineering experience, right? So your goal with your transmission is try to make sure that the motor is spinning more or less at a constant speed, more or less where you have optimal power. And it turns out the optimal power point and the optimal efficiency point are typically pretty close to each other. They're not exactly the same, but they're typically pretty close. Okay, so with these types of systems, you can use conservation of power to figure out the relationships between the motor's torque and, say, the torque being provided to the wheels, right? And that torque provided to the wheels with a wheel of a particular radius, right? That gives you a force, and that's what lets you go uphill, or accelerate, or counter wind resistance. All right, so we'll talk more about drive shafts actually, hopefully by the end of today. But let's take a look at this less interesting problem. Okay? But just imagine that maybe I'm fixing it here, but maybe that's really attached to a wheel. And I've got, a motor that's over here. But it would actually be the opposite, because the motor is going to have this, at least the way I've drawn it, right? The motor is going to be going into like a smaller pinion gear, right? And you're going to have a larger gear that it's connected to, okay? Because you got to reduce the speed. You got to reduce the speed, increase the torque. You all ride bikes, maybe, sometimes, right? You know about shifting gears, right? Or sprockets, or cogs. All right, so let's say that we have these locations marked out A, B, C, D. And we'll call this the B gear and this the C gear. So the first thing is, let's take a look at this geometric compatibility, where we have a linear effective distance of the wheels or the gears. If I have a wheel or a gear with radius R1, and I rotate it by some angle phi1, what's the relationship? How far does it go? If I have radius R1 and I have some number of rotations in phi. Yeah, R phi, right? It goes that distance, right? And if it were one complete rotation, that phi would be equal to 2 pi, and that would be telling us what the circumference is of the circle. The C wheel, or the gear, does the same thing, except it's R2, okay, times phi 2. Okay. Now, they're touching each other, right? They are touching each other. So I already said what the geometric compatibility is here. And then maybe it's obvious here, right? You're like, oh yeah. Do they rotate the same amount? No. But they would go the same distance, right? Because they're connected to each other. So they've got to cover the same amount of distance, and that means that if their radii are different, one may have to rotate more times than the other time. Okay? So this is the first kind of thing to keep in mind. Okay, and we can go a little bit into now what we were talking about with these shafts. Okay, so we'll go into the shafts and then we'll do some equilibrium. So some more geometric compatibility, I guess you could say. This was for the gears. Now we got to talk about the shaft. So if I have a twist of the shaft AB, right, I can write A relative to B, phi. Okay. If I have some twist of C relative to D, I can write it as phi C relative to D. Okay. Now, if I have this end, right? Remember, this is how much do the shafts twist, right? But I've also gotten comfortable writing, say, how much does this end rotate and how much does that end rotate, right? So what is phi A and what is phi B, right? What is phi C and what is phi D, right? They're different than the phi A relative to B, obviously. But they're related, of course, okay? So phi at B, right, is what we'll call phi 1 in this case, right? Does that make sense? That's because it's connected, right? So this is how much that's connected. So the rotation of B at the right end of shaft AB will be phi 1 or phi b. Then I can also look at the rotation at C. Now, the rotation at C, how does the rotation of C relate to anything in this system? The rotation of C, well, it's related to phi 2, right, the way we've written it, because that's not a gear. That's the shaft is mounted right on the wheel, right? So the angle of rotation of the gear and the angle of rotation at the end of the shaft are the same. We also know that D is fixed, right? So D is 0, phi D will be 0. That means that phi 2, phi C are equal to the angle of twist of that shaft, phi CD, right? So we can write phi C relative to D is equal to phi of C, or phi C is equal to phi 2, and this is the rotation of C due to twist in the shaft CD. Okay. I don't know if did I even define the problem properly? I think in the previous slide, yeah. The previous slide we said we're looking at what is phi at the free end of the leftmost shaft, yes. So what are we really interested in? We're really interested in phi A, if we will, okay? And what is phi A? Well, phi A, okay, is going to be the angle of twist of shaft A relative to B plus what? Whatever phi B is, okay? Right? If this were, phi B were 0, then it would just be like this situation that we had down here where phi C is equal to just the angle of twist of the shaft. Okay? So what do we need to do? Now we need to figure out, okay, what is phi A relative to B, right? And we got to figure out what is phi B. And of course, we can't figure those out unless we know something about how the torques, right, internally in these shafts are related to each other. And we can't figure them out unless we know something about how the angle of rotation of this bottom wheel or gear is related to the angle of rotation of the top gear. Okay? Okay, so what is phi B? Well, that one is fun because or at least we can get closer to this, right? Because we said that we have geometric compatibility here, okay? So R1 phi 1 is equal to R2 phi 2. Remember, phi 1 is phi B, okay? And phi 2 is phi C. So here we can write out just the ratio. Phi 1 is equal to R2 over R1 times phi 2. Okay? And we can go a little bit further and we say that phi B is equal to phi 1, and that's equal to this relationship, and phi 2 in fact is the angle of twist of CD. Okay, we said that already. So now we can write out that phi A is equal to phi A relative to B plus phi B, and if I know the angle of twist of CD, then I'm closer, right? But I still don't know what these, so now I don't know what the angle of twist of the shafts are, essentially, right? And we need some ideas about relationships for angles of twist. Well, I know that I can use TL over JG, right? You're like, well, that's not the one I memorized, right? But remember, like, if I know the torque and I know the length and I know the cross section and I know the shear modulus, then I can calculate out what the angle of twist is, right? So, and that's good because now it's down to angle of twists, right? So the angle of twist in A relative to B is going to be this, or a torque, right, which happens to be nicely this torque, right? Because I can take that slice right there and know what the internal torque is, and nothing's happening around it. And this length is L1, and I have a J1 and a G. Similarly, right, phi 2, phi 2 or phi CD, right, is equal to some torque, right, that's being applied either from the wall, the wall, or at this end of the shaft, because they're going to be the same, times L2 over J2G, right? So what's really the unknown here? Do I know everything here? What don't I know here with these two equations? And with this equation? What do I still not know? What do I need to figure out?
We don't know T2 in relation to T.
That's right, right? We don't know what T2 is. Okay, because we do know this T. We knew the dimensions, and presumably they gave us G. Okay, so what we don't know is T2. So how are we going to find Arnold Schwarzenegger? Okay, we are going to use this other point, equilibrium of contact forces. Okay, this is maybe not super intuitive. Do you remember? Well, I don't want to say this. It's not perfect, but early on we said, when we put down Newton's 3 laws, we said, hey, there are. This is not really analogous to that. I mean, there are situations where you do conserve moments all the time, in fact. Right? But in this case, they're not. How do you say it? That gear and this gear are not, or that gear and this gear are not on the same shaft. If they were on the same shaft, then we could say that the torques are conserved. Potentially, right? Where we had to do such. That's kind of fraught as well. That can be fraught. Anyway, the point is, after you're sick of me listening to you going off in the wrong directions, the forces of the contact are conserved. Okay, and this is something important to keep in mind. These are the kind of this is the big thing. So what is going on here? Look, the way to think about this is, let's say I apply an external torque T in this direction, okay, on R1. And so what is this? This is really me looking down into the wall. All right, you see that? Because the way T was drawn here. So I'm looking into the wall, and I've got some phi 1, right, coming around, or phi A, all right? In order for that wheel or gear to be in equilibrium, there needs to be another applied torque to it to counteract it so it's not accelerating. What is that applied torque? It's a torque of this force, F1 we'll call it, okay, applied at a radius R1 away from it. Okay, so now I've got equilibrium here, and that means that T has to be equal to F1 R1. But there's an equal and opposite force then acting on this other wheel, right? So these two forces are equal and opposite to each other. That's third law in action. So there's a force here that's resisting this torque T, okay? And that force that's resisting it is actually applying a force down on the bottom one, okay? And so now the wall, or well, the shaft really, has to be applying a torque that resists the torque due to F2 acting as resistance R2 away from the central axis of rotation. And so now, what do? Now we say, oh, okay, T is equal to F1 R1, right? And T2 is equal to F2 R2, and F1 and F2 are equal to each other. So let's just write it all. So F1 is equal to F2, R1 F1 is equal to T, T2 is equal to R2 F2, and T2 is therefore equal to R2 over R1 times T. Okay. We're almost there. Now is algebra time. Plug T2 into there, R2 for R1 times T. Okay. Plug phi C relative to D into here. Plug phi AB into here. Okay. And what do we get? Something very interesting. We get that this R2 over R1 ends up multiplying this R2 over R1 here. So it's very common when you do these problems that you end up getting an R2, or you get some ratio of radii squared. Okay? Because that comes out of the, like we said, the geometric compatibility for the linear rolling distance of these wheels and the conservation of forces, okay, in equilibrium for the contact between these gears. It's a this is a complicated problem. You know, I think you'd have to be, if you haven't done it before, it's good to get walked through it. Okay, to walk through it. And what's also interesting is that you can, you know, kind of use these relationships plus so what you, how do I say, in a dynamic system, you're not going to be thinking so much about twisting shafts, but you will be thinking about this equilibrium of forces, and you will be thinking about this conservation of power. And when you do that, you still often get this you get this ratio of radii squared. Any questions, thoughts, comments? Yes, Andrew.
Yeah, how did you get that phi A is equal to phi A over B plus phi B?
This one? Yeah. Good question. How do you think? What do you think?
I don't know, it just wasn't obvious to me that like the twist or the angle of rotation on one side is going to be equal to the whole twist minus the other side.
Yeah. So, I mean, some of it is important to think about what this means. Phi A is like a global. It's the global rotation relative to the wall, essentially, where the wall is not rotating. Okay? Phi A relative to B, right, that's kind of a local, right, rotation. That's the deformation only. And phi B is kind of, again, like a global rotation. Right? So phi B is, you know, it's like, look, if I have this shaft right here, which is, you know, whatever this is, and I tell you, oh, it's twisting, right? So I twist, I'm applying a torque, and I get an angle of twist, right? And then I tell you, actually, I'm also twisting this end a little bit, right? Then I got to add this amount of twist to the angle of twist, right? I got to add this rotation at this end, plus the relative twist to get what the final twist on the left is. Does that make sense? Yeah. So that's what that is. But I need to figure out what phi B is. And phi B is kind of a global one, so you know I gotta go on this journey to figure out phi B, and phi B we got because of the gear transmission. But then I have an angle of twist of between C and D, between for that bottom shaft. And to figure that out, I need to know what the torque is in that shaft. Okay, good questions. All right, this is a problem. Take a look, all right, at the solution in 15, exam 1, might be, all right? So we can be grateful that 1, we didn't cover that much material before exam 1, and 2, that I don't think I've put a problem kind of this tricky again. All right, but again, it has to do with equilibrium, all right, and geometry and constitutive relationships. Okay, but I tell you, the answer is there. Okay. Now, this one's a little bit different. Okay, this one also there is. Did I not this? Which there is an exam where this is present on the exam, okay, as well. Okay, this one is saying, all right, we're applying some force here that gets split up between the two wheels, Okay, we have an R3. Okay. We have an R4, all right, which is the radius of the wheel. Okay, and we have this length of the shaft here. Okay, given, and we have an elastic modulus, and we have a nu, a Poisson ratio. So we have to figure out what what G, the shear modulus, is. Okay, and then we're going to figure out what the angle of twist is between gear 2 and one of the wheels. All right, it's going to be symmetric, right, between this. But essentially, what do I need to do? I needed to figure out what the torque is, right? And how do I figure out the torque? Well, I have F, and I have a radius, or I have F over 2, really. That's 5 kilonewtons. And I have a radius R4, right? And so that's going to be the torque on the shaft. And if I need to know the angle of the twist, then I'm going to use TL over JG. And for the TL over JG, which radius do I use? If I'm interested in the angle of twist of the shaft. Yeah.
Radius of the shaft.
The radius of the shaft, right? Which is R3. Okay. Good. All right, now. Oh my goodness. I'm so behind. So behind. All right. All right, so, okay, distributed torsional loading. We already learned about distributed force, right, on a bar. And who was it? Was it you, Matt, who asked that question right before the exam? Were you glad you asked that question right before the exam? Yeah. Yeah, I was glad you asked that question right before the exam too, right? Hopefully that was a learning experience, right? But the idea with a distributed force on a bar, right, is that you do the integral of the lowercase f dx, I think as Kira pointed out, right before the exam, okay? And that gives you an idea of how to figure out a balance, right, for the internal force. What we're going to do here, we're going to use some relationships for the distributed torque to figure out what the internal torque is as we move along, right? So here we go, right? Before we had an f dx, now we have a lowercase t dz. And this lowercase t has torque per length, okay? So the overall torque, over a span, z, is tz. Okay, this is useful too, right? If you have a section that's just along for the ride, okay, which you did, but it was with experiencing 0 force on the exam, right? That section was just like, just along for the ride. But if you have, that's maybe not, it's not along for the ride. It's if you have a section that has, that does not have the distributed force, okay, but is experiencing a distributed force or a distributed torque applied to another section. So for example, let me just put it this way. Let's say that you magically somehow you had gravity here acting down, but no gravity here. Okay? And I gave you that this length here was L2. Yes, you had to use a distributed load on this section, but what would be the force, what would be the internal force in the top? Any ideas? I have gravity acting here. It's not, it's acting on the bottom section. Somehow it's not acting on the top. What's the internal force? Yeah. These are not the drones you're looking for. That's not the answer I was looking for, okay? It's not 0. It's what?
Isn't it equal to the weight of
Yeah, it's equal to the weight, right? If gravity is applying here, right, it's equal to the weight of this section. This is also essentially, so, you know, one is, okay, just figure out what this mass is, M2, right? And, you know, you're like, oh, well, I know it's rho times G times the volume of it, right? That would be the weight of that section. Or, you know, you're like, if you use our relationships that we've been talking about, and I tried to spell that out on the exam, not that you weren't supposed to use gravity on the exam, right? It was a distributed force, but I just wanted people to see that if I have rho G, the distributed force is actually rho G A, right? And then I put it in the integral. Right? And so then it ends up being rho G A L2. Okay? Which is just the mass. So that's one thing I wanted to point out. In the exam, it was 0, so you good, all right? Okay? But in situations where you've got a distributed force acting and pulling this down, just think back to I've got a spring and I'm dangling a mass from it, right? That's the force in that member, right? And I just want to point out that yes, we have all this fancy stuff, but if it's a constant distributed force or constant distributed torque, just do, and I put that on the exam, put distributed force times length, distributed torque times length. And that's going to give you what the internal force, I mean, there could be other things beyond it, but that gives you what the applied load is, at least from that distributed force, acting on another member that's got nothing going on in it. Of course, this is more complicated if I want the overall displacement, because then I got to do, right, rho G L squared over 2. Rho G L squared over 2E. Okay. Or G, yeah, right? So that's one of the relationships. Okay, but if it's a distributed force, then it's like F, I don't even remember. It'll be in the solutions, but it's like, F squared or something. No, it's FL squared or something over 2EA, something like that. Okay, so angle of twist, okay, can be found by thinking about the internal torque, okay, and using the distributed torque to figure this out. So the angle of twist. Now, this works out, but it's not as faithful as this. This is the more careful approach, okay, where what we say is that I'm going to break up this shaft. I'm going to look at the internal TI. I'm going to do equilibrium. And this is going to give me the same answer, but this is the right way to do it. This is kind of a shortcut that works, but it's using the external torque directly. This is a better, more careful way to look at the problem. Okay. I should probably delete the previous slide, but this is, but this is how you should go about doing it. What do I mean? Look at the external distributed torque's effect at creating a TZ. Look at the reaction torque, which is external, and then look at the internal torque, TI, which is the one for which we are solving, and TI is the one that we put into the angle of twist formula. Okay. All right. Statically indeterminate torsion. Okay. So equations of equilibrium are insufficient to determine torsional loadings in indeterminate torsional cases, right? This is just like something else we've seen, right? Take two bars, take two bars and just attach one wall to it as a determinant problem. Add another wall, you add another constraint, then you have more unknowns than you have equations if you only use equilibrium. If we use more than equilibrium here, we use our constitutive and we use our geometric relationships, right? Then we can kind of attack this this problem. Or we can think about so this is just saying, this is just equilibrium. It says, hey, look, we can't solve it. Okay, we don't know. So what we have to do, we can use our geometric compatibility. And the end-to-end relationship between the angle for the overall angle of twist is pseudo, right? So that's nice, but it's also, we know that the angles of twist, right, of A to B and B to C, they're going to be adding up or adding up to or equal and opposite of this, like that. All right. Constituent relationships, we know TL over JG. All right, so that's what we use here. And I'm sorry, I'm kind of speeding through this because I want to at least have you be able to do or take a shot at this homework. All right, and we can go ahead and we can write out these two relationships. Okay, we have now geometric compatibility, we have constituent relationships, and we had some questions about what the torques were. So we can combine equations. All right, we're going fast here, like we do here. Okay, and now we have another equation that relates these torques to each other, right? So we can combine this with static equilibrium, which we had on the previous slide. Okay. And when we do that, that's just copy and paste. We can then finally write out relationships for the torques and figure out angles of twist, if we so desire, for those individual members. I think in this I won't go back, but the point was to figure out what the torques were in the individual members, and then you can do things like stress and twist. Okay, indeterminate shafts with mating gears. All right, take a look at this. I'm going to jump over, but this is it's intense. All right, this is like that same type of problem that we did before, right? That was a determinant system. This, well, yeah, it was not really, how do you say it? We were looking for angles of twist, so we needed to use we had to use our constituent relationships as well. But this one's even more complicated in that we have two walls and now we're applying a torque in between. Okay, so you can take a look at this. This one, all right, is also from a previous exam. It's, I think, a COVID exam, so I think this would have been fall of 2020. So take a look at that one. All right, and then tomorrow we'll do the finite element. Okay. That was a lot. I had to speed up at the end. All right, so take a look at the homework. If you have any questions, let me know. I will make sure that we only go through Q6 tomorrow, so there's 6 questions, and there are still some left over from the first one, and then we'll go over Q7 tomorrow in class. All right, have a good one. If you missed out, I think was everyone here at the beginning that's here now? Thursday, it's optional day, all right, to come, but you'll get credit because I'm only going to be here for half because I have to run to a meeting. And then Monday and Tuesday are going to be virtual, all right? And there won't be attendance, but I'll have the videos and stuff. And I can communicate over GroupMe if there are questions. Okay. All right, see you tomorrow. Thank you.